Hello, I'm going to talk to you about direct air capture, a technique of trying to reduce the quantity of carbon dioxide in the atmosphere as a way of reducing the greenhouse effect and the degree of warming. This is something which is becoming increasingly obvious that has to be done, because we cannot depend on the reduction of our carbon emissions for doing anything about global warming, because carbon emissions of any kind still allow the atmosphere to continue to warm, and the atmosphere is already too warm. So the only way of actually bringing down the air temperature is to actually take carbon dioxide away. And this method involves taking it away directly from the atmosphere. It's based, some description of how this works is found in my book, Farewell to Ice, which is published by Penguin. And also, there is a very good movie about the process of air capture and about global warming in general, called Ice on Fire, which is made by Leonardo DiCaprio and contains material on many of the scientists who are working with this problem all throughout the world. So it's a film that can really be recommended. Of course, our inspiration in all of this is Greta Thunberg, who has forcibly drawn the world's attention to the fact that this problem is the central problem facing humanity, and yet is not being treated with the seriousness that it deserves. Now, the story begins with the best and most honest record that we have of the warming of the planet, which is the record of carbon dioxide content of the atmosphere measured from the Mauna Loa Observatory in Hawaii on the top of a mountain. And this set of measurements began systematically in 1958 with Keeling and has been maintained ever since. And when we look at the record, we see this rather sorry tale that the little red wiggles are seasonal variations in carbon dioxide, but the black line is the background trend, and we can see that that is accelerating upwards. And since global warming is dependent on CO2 content, what this is telling us is that the warming of the atmosphere, the warming of the planet, is continuing to increase, and at an accelerated rate. It doesn't matter what we say we've done, we haven't actually done anything. Here we see the record again with a couple of data points at the top there, which show that in a typical year, the carbon dioxide content increases by about 3 parts per million. Now, given that the overall and total carbon dioxide content was only 280 parts per million at the end of the last ice age, and even by 1960, it had only gone up to 315 parts per million, clearly the accelerating upward trend is really going to be disastrous for the planet. We can't tolerate an extra 3 parts per million every year. We reach a point where the amount of warming is far too great for the planet to stand. And also, everything that we think we've done or that we claim to have done has been not valid. This is the upward curve, and the little markers along the way are the dates of COP meetings of that's Committee of the Parties of United Nations, and we can see that at each COP meeting, nations make commitments to reduce their carbon emissions, and the most recent and the biggest agreement was the 2015 Paris Climate Agreement, which is the second marker down, but it seems that that had no effect on the slope of the curve, and we see the white lines are showing that as time goes on, the upward slope of this curve increases, so that global warming is accelerating, has been accelerating ever since we started doing our measurements, and is continuing to accelerate now. And it's not only carbon dioxide. There's also methane as a component of global warming. It's a greenhouse gas, second only to carbon dioxide in its impact on the planet. And methane itself has a very variable content because it comes from so many different sources, from animal digestive processes, from leaks in pipelines, from rice cultivation, from a whole range of man-made and natural sources, which means that we can't really easily predict what the methane content is going to be. We can only record it, and we can see that it has gone up and has started to accelerate upwards quite significantly. The blue lines here are the seasonal variation in methane measured at a site in the Arctic, in Alert, the northern end of Ellesmere Island. And we can see that there's an annual cycle, but that the average methane content had reached some kind of peak, some kind of steady state, from which it's now departed in an upward direction, and methane itself is now accelerating in its content in the atmosphere. That's the red line, which shows how it's gone up since 2014. So why is this going on? Well, we have the problem of excessive emissions of carbon dioxide. And when we look at the different nations and try to find the guilty parties, we see the main guilty party is China, with this very rapid increase, the red line here, and with India following along second. Until recently, the USA was the largest single emitter of carbon dioxide in the world, but it fell behind because China overtook it. Similarly, Europe, whether we look at all the nations of the EU or just some of them, has also flattened off. The reason is not because Europe and the USA are very good at controlling their emissions. It's because the factories which emit a lot of carbon dioxide have been moved to China and India. So China's taken over the USA and Europe's function of being the big carbon dioxide emitter. But if we add all of these together, we're getting a continuing exponential increase in carbon emissions. You'll notice in this diagram, we say fossil fuel and cement, because cement is a very special villain in this area, since the process of cement production itself involves carbon dioxide production from the chemistry of it, and carbon dioxide production from the energy requirement of cement factories. So cement is a very special villain, and we should be minimizing our use of cement, especially we shouldn't be building buildings out of cement, but we are. Well, that's the situation. It looks bad and it's getting worse. So what can we do about it? Well, the first thing we can do is reduce our carbon emissions. And this is what the nations of the world have promised to do under the Paris Climate Agreement. But first of all, they have to keep that promise. And it's difficult for them to do so because it's easier to simply continue your fossil fuel use and produce carbon dioxide. So we have a difference between what big countries promise and what they deliver. And even the best that can be done involves some carbon emission from fossil fuel burning. So the trouble it being that carbon dioxide remains in the atmosphere for thousands of years. So whatever we emit remains in the atmosphere and remains to continue to warm the Earth. There isn't any way that it will go away. So we have to stop producing it, but we can't do that. We are slaves to the fossil fuel culture. And so that seems to be a conundrum that is insoluble. But in fact, there is a solution, and the solution is to take carbon dioxide out of the atmosphere by some chemical means. This will allow us to bring down the carbon dioxide content and bring down the amount of heating and warmth. The Paris Agreement calls for an effort to slow down the warming rate to 2 degrees by the end of this century. And now we see the harmful effects of increasing CO2 in climate disasters and weather events. We want to try to keep the warming to 1.5 degrees, an even tougher target, and one which many people feel, many scientists feel, can only be achieved by removing CO2 from the atmosphere, not by reducing emissions. And so if we do that directly, we call that a technique like that direct air capture. We can try taking it out of the ocean instead, but the principle is the same. Also, there are techniques which don't remove carbon dioxide, but do suppress the radiation effects of carbon dioxide. And those are called geoengineering methods. So I'll address these as well. In fact, I'll address these now. They count as a kind of stopgap between doing nothing and taking carbon dioxide out of the atmosphere. And one of the most promising methods is being developed here in Scotland, actually, by Stephen Salter, a scientist at Edinburgh University, who found that if finely divided water particles are pumped out of a fine nozzle into the lower levels of marine clouds, then that makes the clouds brighter because of all the very small particles going into the cloud, which increase its brightness. And when a cloud gets brighter, it reflects more radiation and back into space, and that cools the atmosphere. So the design of equipment that he recommends is a series of floating unmanned vessels, sort of drone ships, which look like this picture. The three masts are actually Fleckner rotors, which rotate and supply the drive to the ship to take it where you want it to go. And inside the Fleckner rotors is the hollow mast where seawater is pumped up to the top of the mast and goes out into the lower part of marine clouds, stratus clouds, which have low bases. And it's calculated that this would 40 of these would be sufficient to keep the Arctic cool, and 200 would be enough to keep the world cool. The CO2 is not affected, so we still will have some other harmful effects, like the increase in the acidification of the ocean from the dissolving of CO2, but at least we would have a lower amount of warming due to the reflection of radiation into space. So I think, and especially because the seawater is completely non-toxic, I think this is a remarkably promising, excellent method for acting as a stopgap in global warming. And I think it's absolutely shameful that that has not been supported by a large amount of funding, especially in his own native country of Britain. What else can we try to do? Well, there are various other techniques being proposed, but all of them have drawbacks because of when you scale up to global size for a given technique, you have to cope with the difficulty of doing things on such a large scale. Here's a number of techniques, the three other techniques. And the simplest one, of course, is afforestation. The idea is, well, you plant a tree, you plant lots of trees, you plant 1 trillion trees. Trees do absorb carbon dioxide, and so the more trees you have, the more carbon dioxide you absorb. But if we look at the amount of the area of trees necessary, then just to deal with the warming caused by fossil fuel use in Europe, we would need to plant an area of trees of 6.4 million square kilometers, which is the area of Europe. So to get rid of Europe's carbon dioxide, we would have to completely cover Europe with trees, which of course we can't do. Then there are other methods, each of which also involve not only large costs, but large amounts of area used up. BECCS, for instance, which is an acronym for bioenergy in combination with carbon capture and storage. That's you actually grow biofuel, you then burn it and capture the carbon dioxide that's produced. It seems a cumbersome method, and it is, and it also requires a large amount of area. And a very slow method would be to crush silicate rocks, and which as they very slowly weather, they remove carbon dioxide. All of these are either very slow, like enhanced weathering, or they require huge amounts of land, like afforestation. So we're left with direct air capture, that is, using technology to suck carbon dioxide out of the atmosphere and reduce the level, and thereby reduce global warming. So, as I've said here, it's the only ultimate solution as far as I can see. And since our CO2 levels are already too high, then this technique can be used to bring the level down if we use it with a high enough intensity of effort. At the moment, techniques have been developed which work, which are fairly simple technology. It's not miraculous science yet to be developed, but the cost is too high. It's coming to about $100 to $200 a ton of carbon dioxide, and we need a method that will cost less than $40 a ton, because that's about the amount of damage which we do by carbon emissions. So we want to bring the cost of these systems down, and of course, with experience shows that if a new technique is applied with enough energy and enough time and effort, it can become much more efficient, just like solar energy became much more efficient and cheap over the years until it's become one of the cheapest sources of energy from being one of the most expensive. So we hope the same would happen with direct air capture. We've got methods which work, but which are too expensive and which can be therefore, hopefully, improved by some technical development. But let's look at the basis first. And the basis is that man is putting 42 gigatons of, that's 42 billion tons of fossil fuel and carbon into the atmosphere per year through burning fossil fuels. So if we're going to achieve an impact on this, we have to remove at least 42 gigatons per year, hopefully more than 42, so that we bring the level down rather than have it rise. And as I showed in from this earlier curve, so far there's been no real efforts at reducing emissions that show any sort of impact. More lower is our honesty box. It's what shows us that we are not, as well, for all of the talk of politicians, there hasn't been an effort which has produced any noticeable effect on carbon dioxide content of the atmosphere. But this would be how a system would work. We blow air over collectors which chemically absorb carbon dioxide out of the air. This is called a capture solution. That is it's usually an aqueous solution of a chemical, which can be a very simple one, like sodium hydroxide. And that capture solution, then the carbon dioxide contained in it is separated off by evaporation and turned into something which we can use. We either compress it and pump it underground, that gets rid of it at the cost of having to deal with an underground disposal site, or we turn it into something else by another chemical means, something that can be used. One of the methods that is most promising involves turning it into artificial limestone. But here's the sequence. Direct capture of this carbon dioxide from the air, turning it into some kind of solid material, in this case pellets, and then taking that away and using it for something. The methods that have been tried up to now, the most promising one as far as I can see is done by a company called Blue Planet in Los Gatos, California, where it's converted into limestone. Now, there's a huge need for limestone because it can be ground up to produce sand, and sand is a material which surprisingly is in scarce supply for building, because you need sand for cement production, and the sand is very special sand, not just a shortage of sand. And the limestone that we can produce when ground up is exactly the right kind of sand. So that's one method which produces a desired and useful product. Another method is simply to pump the carbon dioxide underground into rocks which chemically latch onto the carbon dioxide, basalt rocks, and then it's permanently sequestered in underground caverns. So caverns made of basalt rock, some very convenient ones are situated in Iceland and are being exploited by a Swiss company called Climeworks. So there are other countries besides Iceland where this would work. So sequestering carbon dioxide in rock is a very viable technique. And the biggest working case of this at the moment is at a geothermal energy plant in south of Iceland, Elisheithie. A third technique involves turning the carbon dioxide into jet fuel. This seems at first sight to be not a good idea, because we're removing carbon dioxide from the atmosphere and then we're turning it into something we can burn, which is jet fuel. Seems a bit pointless, but in fact, of course, the reason is that at the moment we don't have a good viable way of powering aircraft by non-fossil fuels. We need those liquid fossil fuels for the engines of aircraft. So if we can make that fuel out of carbon dioxide from the atmosphere, we're at least achieving neutrality. And the company that has pioneered this is called Carbon Engineering in Squamish, which is in British Columbia, where they can make use of hydropower as the energy source for the process. Let's look first at the method of turning the carbon dioxide into limestone. This is the end product of the process, where the CO2 that's removed from the atmosphere is reacted with lime, with calcium oxide, and the result are these nodules of of limestone. There they are in the reaction vessel, as they're produced. And one of the attractive things you can do with these limestone nodules is incorporate them in cement or concrete and produce a kind of concrete aggregate, which the technician is showing here, a concrete aggregate in which the production of this aggregate involves a reduction in carbon dioxide level, because we've used carbon dioxide out of the air to incorporate into the aggregate. So concrete, instead of being a very wasteful material, can be made into a very productive material. And they've demonstrated this by using concrete made from limestone that's removed from the atmosphere to re-roof one of the airline terminals at San Francisco Airport. So here it is being poured over the roof, and it's worked very well and produced a carbon negative building, which is a remarkable achievement. Now, what about Europe? These advances are occurring in the US, although they're trying to transfer the technology to Europe. And a plant was started in Italy, in Apulia, with a sort of pilot plant shared with the Polytechnic of Turin, Politecnico di Torino. The pilot plant will only filter 150 tons a year of carbon dioxide, which is not much, but it's just a start. And at the same time as producing carbon dioxide, an alkaline electrolyzer locally will generate renewable hydrogen, and the hydrogen will react with the carbon dioxide by a technique called power to gas, or catalytic methanation, which is a French developed technique by a company called Atmostat, which then produces methane, and the methane can be liquefied and used as a fuel for natural gas for lorries. So we're taking the carbon dioxide out of the atmosphere, reacting it with hydrogen to produce methane. That's the basis of the technique developed in Apulia, and the moment the development has been halted because of COVID. But hopefully that will continue, and the technical expertise of the Politecnico di Torino can then be deployed to make the process more efficient, which is what everybody's seeking, a more efficient process which costs less per tonne of carbon dioxide that's released. This shows the plant of Climeworks, a Swiss company, in the south of Iceland, where energy, geothermal energy, is used as the energy source. All of these processes require energy to be done. And this is one of the drawbacks of direct air capture. You have to use energy to get rid of the carbon dioxide. And of course, the energy mustn't be produced by fossil fuel burning, otherwise we produce the carbon dioxide as fast as we use it. So in this case, we use geothermal energy from the earth to do the process. And fortunately, Iceland has got a lot of caverns. It's a volcanic region, and the carbon dioxide can be pumped underground, where it couples with basalt in these caverns to produce a permanent rock, which gets rid of it. This is showing just one of the systems for getting rid of the carbon dioxide. The air is blown over the absorbing solution. Now, the other technique that I mentioned is called Airtofuels technology. So this is the same thing. It takes the carbon dioxide out of the atmosphere, and but also has a side plant which uses renewable energy to generate hydrogen from water, from electrolysis, combines that with the carbon dioxide to produce these hydrocarbon fuels, which diesel, gasoline, or jet A, in which we can actually burn, but burn in a location or method which we wouldn't usually be able to use, like burning in a jet aircraft. And then we achieve a neutrality. The carbon dioxide is removed from the atmosphere, is turned into methane, is then burnt, and we have a neutral system. So the pilot plant there is in the mountains of British Columbia, and again, it's there because it can use hydropower from mountain lakes as the source of energy for this very energetic, intensive process. So they are building larger and larger batteries of collectors. You can achieve more or less an infinite increase in the numbers of collectors. And of course, we'll have to do that all over the world. We'll need many, many plants like this, taking carbon dioxide out of the atmosphere. That's the necessity that the world is facing up to. Here's just the present construction, which is just a battery of these, but we'll have to see huge plants in which thousands of collectors are deployed. This just shows the inside of the plant in processing. So we can see both for carbon engineering and for other techniques like Blue Planet, we have to have a reactor where the air is brought into contact with an absorbing solution. The absorbing solution is turned into a solid, in this case pellets. The calciner, in this case, takes those pellets, turns them into hydrocarbon, and the slaker then takes you back to the original material, the original slaked lime, which is the source of the energy. So you scrub the material with hydroxide solution, convert it into a carbonate. The pellet reactor turns the carbonate into small pellets of calcium carbonate, which are then heated until they decompose and release the carbon dioxide as a gas, which is then used or pumped away. So you then, the reaction then goes round in a circle. So that works. I'm going to end by talking about other techniques, one of which is being developed, has been developed for some time in different places. It's called biochar production. And this shows a plant in California which uses agricultural waste, in this case pistachio nut shells, and this company is called Hago Research in Camarillo. And the shells, which are organic material, are, instead of being burnt, are digested in this apparatus here with low level of oxygen, and that produces a kind of oily substance. It produces a solid called biochar, which can look something like charcoal and can be spread on fields to fertilize them. And the process takes carbon dioxide out of the atmosphere. So it's like CO2 removal using direct air capture, except it uses this pyrolysis of digesting a biological material under reduced air content. So their pilot plant is very successful, and in fact has been incorporated in the energy system used in a branch of the University of California in Ventura. So it is the first university which is powered partly by pistachio nuts, which is quite amusing but very important. Anyway, all of these costs are still too high. Carbon engineering think that the system costs between $90 and $200 per tonne. We want $40. So we need further technical development to bring the cost down. Also, the quantities are very small. Carbfix, which is the system used in Iceland, is producing tens of thousands of tonnes a year. Now that sounds a lot, but remember we've got to get rid of 42 billion tonnes, which means we're going to need thousands of these plants all over the world, and we do need them. We have to have them. We've got to get rid of that carbon dioxide. We can't live with an increasing carbon dioxide level in the atmosphere. It's going to kill us off. So we have to find a way to get rid of it, and these methods work and must be developed more intensively so that they can be done in a less costly fashion. Remember also that the process involves energy, so we have to find a source of energy to power the carbon dioxide removal plants. In the cases that have been tried so far, we use hydropower or we use geothermal energy. We've got to use something other than fossil fuel, otherwise the process is pointless. So this development is very, very important, but like so much in the way of saving the world, it's not being funded at the level required. But there's some support coming from foundations. And one is the Foundation for Climate Restoration in California, which is close to the location of the Blue Planet company. And that's led by Peter Fikowski in Los Altos. And there's the Climate Repair Centre in Cambridge, which is led by Sir David King. And so what that tells us basically is we can do it, we have to do it, because without it, with carbon dioxide levels continually increasing just because we burn fossil fuel in whatever small quantities, if we burn it at all and CO2 increases in the atmosphere, we're lost. We're on a downward path. And we can see already the effects on global air temperatures, on processes which result in disasters like floods and hurricanes. And we can see it in the reduced habitat for creatures and wildlife on the planet. I mean, an extreme case that is always cited, and which I know about because I often go to the Arctic, are polar bears. Polar bears can only live by hunting seals, and they hunt seals on the sea ice. And to survive, they have to be able to find sea ice to hunt seals on. And the sea ice in the world is decreasing rapidly in area, and polar bears are being reduced in their habitat to quite a narrow fringe of sea ice around the high latitude edges of the Arctic in the north of Greenland and Ellesmere Island. So we're in danger of losing polar bears, which are the very top of the food chain and are in fact magnificent creatures. So many other species are threatened in the same way and are also being lost. Even as we look at them, they're disappearing from our planet. So we have to do something about this. We have to do something about the whole problem of CO2 increase and also methane increase, of course, and what it's doing to global temperatures. So there's where I hope that the world will take a second step in common sense. The first step, which took many, many years to bring that level of intelligence to the human race, was we've got to stop emitting carbon dioxide. We've got to stop producing so much of it from burning fossil fuels. Now that lesson has gone home. I mean, it has actually affected people. We, in theory, are reducing carbon dioxide emissions. As I've shown, in practice, we're not. But the will is there, even though it hasn't turned itself into anything useful in the way of carbon dioxide reduction. But the world has realized this is a need. But what it hasn't realized is that that is not enough. It's not enough to take carbon to reduce our emissions of carbon dioxide. We have to take carbon dioxide out of the atmosphere. There are other methods to do it, which I haven't mentioned, which involve removing the carbon dioxide from water and from the ocean. Those are promising as well. This one is directly removing it from the atmosphere, which is what looks like the simplest thing to do. We can do it. The technology is there. There's no unknown science involved, but the method must be improved technically so that it becomes cheaper. And then we can build thousands of these plants, which is what we'll need to hold back and actually, in the end, reduce the level of carbon dioxide in the atmosphere. In the meantime, we have these stopgap sticking plaster methods like marine cloud brightening to prevent warming from getting out of hand. These techniques will and can save us, but simply reducing carbon emissions can't save us. And I have to say that with as much strength as I possibly can. It's no good in the end just reducing carbon emissions the way that officially we're doing under the auspices of the International Intergovernmental Panel on Climate Change. That's not enough. We're being misled if we think that we can get out of our climate crisis by reducing emissions. We can't. We have to take carbon dioxide out of the atmosphere. So let's go ahead and do the research we need to do and build the plants that we need to build to make this possible. Thank you.